Precalculus, Unit 1, Day 1. Let's start it off right now. Day 1, we're talking about functions. So we're going to look at what is the definition of a function, and then we're going to do some stuff with functions. So before we get to functions, we want to talk about relations just for a second. Okay? A relation is any rule that relates to different quantities. If you look at a relation on a coordinate plane, a relation is just a scatter plot. It's a bunch of x's with y's. So for every input, there's an output. Every x, there's a y. Okay, and it puts it in a couple of ways. Everything in the domain or in set A has a corresponding element in the range or set B. Okay, your x coordinates are going to be your range, your domain, and your y coordinates are going to be your range. Okay, domain x, range y. Okay. Now a function is a special type of a relation where each x has only one y value. Okay, so if I say in this function or in this relation, when x is 1, what is y? And you give me one answer and only one answer, that's good. It might be a function. If I say, if x is 1, what is y? And you say, well, there's 1, 3 and 1, 6. Oh, there's two answers for a y that corresponds to a certain x. Okay? You can't have the x repeat. You can't have 1, 3 and 1, 6. That immediately tells you it is not a function. All right? I know you've heard all this before back in Algebra 1, definitely in Algebra 2. So, I'm not going to dwell too much on it, but, you have your vocabulary of function. You have your vocabulary domain, which is all your x values. Range is all your y values. Okay? 4 ways to represent a function. You can say it. You can verbally state. Okay? A sentence that describes how your x's and your y's, your inputs and your outputs are related. So the output is 2 more than the input. So that would look like y equals x plus 2. Okay? The output, your y, is 2 more than, so something plus 2, than the input, so x plus 2. So y equals x plus 2 would be an example of this. But verbally, it's just saying it in words. No algebra. Algebra comes down here. Right? You can do a graph. You can plot your points. You can have a table. Okay? So you can represent a function numerically. Okay? You can, as we mentioned with the verbal one, algebraically come up with an equation that may show your relation, your function. Okay? So if we scoot down this page just a little bit, we see 3 of the different methods of expressing functions or relations, and we want to see if these relations are functions or not. So first we have the table. So that's a numerical representation of a relation. So we're going to just see if x is 9, what is y? How many answers? You give me one answer, y is -3. If x is 1, what is y? Well, take a look at this. If x is 1, your y is -1. But if x is 1, you also have a y of +1. So because you have 2 answers for what is y when x is a certain value, that immediately tells you this is not a function. You can go on and look at the 4 -2 and the 4 +2. Those will also tell you that this is not a function, because when x is 4, you have to have one answer for what is y. Every input, x, must have only one output, y. So this x repeats. This one is not a function. So if you look at question 2, question 2 is a graphical representation of a relation. And here we're going to be looking at, again, every x can only have one y. And you have the vertical line test that you can use to test whether this is a function or if it's just a relation, right? So if I draw any vertical line anywhere, do I intersect the graph in one point only? If I ever intersected this graph more than once, then that says it's not a function. Okay? Every one of these vertical lines seems to intersect the function in one and only one point. If my graph had been like this, then you did your vertical line and you say, oh, that vertical line intersects twice. That's not a function. Okay? However, the one that was given to you does seem to be a function. Okay? Algebraically, this is a nice algebraic equation. Okay? Nice way to do these and really be sure of them. If you solve for y, okay, you're used to y equals, like y equals mx plus b. If you go all the way back to algebra 1, a little bit of geometry. Let's solve for y on this one. And I'm going to show you something that's a key factor in being able to tell that something is or is not a function by looking at the equation. So if I'm going to solve for y, first I have to cancel out that 3. So I'm going to divide both sides by 3. Right? So I've got y squared on one side, and I've got x over 3 on the other side. Now, we're going to have to cancel that squared. Now, how do you unsquare a squared? Well, you take the inverse operation. If you look at your calculator and you see the x squared button, you'll notice in the blue for this particular calculator, right above the x squared button, written down, is a square root, because those two functions are inverse functions. They undo each other. So here, I'm going to take the square root of y squared. And the square root of y squared is going to be y. Okay? On the other side, you have to do the same thing. You have to take the square root. And here's something you're going to hear me say well over 100 times this year. When you take the square root of both sides of an equation, you have to plus minus your answer. Okay? So y equals plus or minus the square root of x over 3. I'm going to just leave it like that. I'm not going to worry about rationalizing the denominator of the square root of 3. And I'm just going to say, look at this. When I have plus minus, that tells me that there are some x's that are going to give me 2 y's. For example, if I say x is 3, when x is 3, I've got 3 over 3, which is 1, and I got the square root of 1, which is 1, but my y is going to be plus or minus 1. So that means we got 3 comma 1 and 3 comma negative 1. That immediately tells me I've got 2 y's for 1 x. Can't happen. Okay? So this is not a function. And the indicator that I would say you look for is the fact that there's a plus minus. If there's a plus minus in y equals, then you know that's not going to be a function. Let's look at the next. Okay, so on this page, we are looking at function notation. Right? I believe we've at least looked at f of x. I believe in algebra 2, you were introduced to f of x. F of x is just an elegant, classy way of replacing y. So f of x, a function of x. Instead of saying y equals mx plus b, you could say f of x equals mx plus b. Right? So f of x is read f of x. It's not f multiplied by x. Right? So f of x, as I just said, is the y value. Right? So we used to say y equals negative 6x is the equation of a certain line. Now we're in precalculus. We're going to say f of x equals negative 6x. Okay? Just make it seem a little fancier for us. So x, again, is the independent variable, usually the number that you plug in, that you substitute. And y, or f of x, is called the dependent variable. Okay? Kind of nice. Right? Evaluating a function. Now let's just do some pre-algebra stuff. Okay? By substituting values in for x. Okay? So now instead of f of x, we're going to find out what f of 3 is. Okay, and you did this in Algebra 2, I know, but we're going to have a lot of review. So f of x is x squared minus 2 times x minus 8. Well, f of 3, all we're going to do is substitute the 3 for the x, because it's not f of x, it's f of 3. So f of 3 is 3 squared minus 2 times 3 minus 8. So you see we took f of x and we replaced the x with 3's. Now we're just going to PEMDAS, we're going to use our order of operations, and we are going to evaluate what f of 3 is. So 3 squared, we're going to do the exponents first, is 9. And then we can do the multiplication. So 2 times 3 is 6. So f of 3 is going to be 9 minus 6 minus 8, which is negative 5. Okay, easy peasy. Same f of x, but now we're going to say we're going to find out what is f of negative 3d. So nothing to get terribly scared of here. Negative 3d is going to replace or be substituted for x. So instead of x squared, it's going to be negative 3d squared minus 2 times, instead of x, it's going to be negative 3d. And then we're going to have minus 8 at the end. Now we're just going to simplify. Okay? We're back into simplifying an algebraic equation here. So we're going to take the exponent, negative 3d squared is negative 3d times negative 3d, which is 9d squared, minus 2 times negative 3d, that would be a plus 6d. And then you have your minus 8. Okay, do we have any like terms? This has a d squared. This term has a d. This term is a constant with no variable whatsoever. So this is your final answer for f of negative 3d. All right, I'm going to do a little erasing here, so you can pause and rewind if you need to write this down. Just going to erase this out. Right. We're going to do the same thing once again, but we're going to substitute 2a minus 1 for x in f of x. So we're still back here. So f of 2a minus 1, I'm going to start it on the next line here because I know I won't have enough room. Okay. This is finger on iPad, so I'm not going to be able to be too precise here. All right, so instead of x squared, it's 2a minus 1 squared minus 2 times 2a minus 1, then minus 8. Okay, straight substitution again. Now we need to evaluate by expanding. Okay, so we remember that squaring means something times itself. 2a minus 1 times 2a minus 1. Okay, I'm going to do that off to the side up here. 2a minus 1, I'm going to square it by multiplying it by itself. If you remember how to FOIL, first, outer, inner, last, it's just a distributive property. So 2a, we're going to multiply it by 2a and by minus 1. Okay. So 2a times 2a is 4a squared. 2a times minus 1 is minus 2a. And then we would take the -1, and we're going to distribute that. So you have your F and your O, now you got your I and your L. Okay? You did the first and the outers, and then now you're going to do the inner and the last. Okay? So we've got -1 times 2a, so that's another -2a. You got -1 times -1, which is +1. Do we have any like terms? We do this time. We have two terms that both have just a's in them for the variables. So let's combine them. We got 4a squared minus 2a minus 2a. Well, -2 minus 2 is -4 or -4. Let's put that squared there. Minus 4a, and you got your +1. Okay. No like terms, can't add them or subtract them and combine any like terms there. Right? So that is it for functions being evaluated. Okay, so we did a little FOIL, did a little simplifying, a little evaluating. Let's go down to finding domains and see how we do with this topic. All right, now this particular part of day one is the part that people get confused with every year. You're going to benefit by having the video so that you can rewind and fast forward and whatnot. So really take your time on this. Make sure that you understand it and ask questions if you don't. Right? So when they say, what is the domain of a function? Okay? The domain of any function that's written here is usually not going to be anything except for all real numbers, which when you learned how to do interval notation looked like this. It looked like -infinity to infinity. Okay? A lot of functions are going to have -infinity to infinity. The only two things that can limit your function so that it's not any old real number. You say, well, what are you talking about domain of a function? Remember back at the beginning of this notes, domain means x values. What x values will give me a real number y value? That's all it's asking you. So when would you not have a real number? There are two times. There are two instances. One instance, and we bolded it and underlined it. One instance is if I have an x that makes it so that I'm dividing by 0, that's not a real number. The second instance is if I have an x that's going to make it so I'm taking an even root, like a square root of a negative number. That's not going to be a real output. That's not going to be a real number for y. So for the domain of a function, it's going to be any time where those two things are not happening. There's no dividing by 0, and there's no taking an even root of a negative number. Okay, I think that once we do some of these, it's going to make a little more sense to you. So let's check this out. Okay, so question 1. Okay, g of x equals the square root of x minus 3. Okay, a lovely looking function. Is there anything there that could possibly make one of these two things happen? Okay, is there a fraction where the denominator has an x in it where I can make that denominator 0? No, there's no denominator here whatsoever. Okay, is there a square root with an x in it where I could have an x value that makes me take the square root of a negative number? Yes, there is. So what we do is this, okay? Follow this, replay this as many times as you need to get this through your head and to get it to stick. You're going to take the radicand, which is just the stuff inside of the radical. So in this case, it's x minus 3. This x minus 3 must never be negative. So that means it could be positive, which means greater than 0, or it could be 0, because the square root of 0 is 0, and 0 is real. So it's greater than or equal to 0. So now all you need to do is solve for x. Okay? So I add 3 to both sides, and I get x is greater than or equal to 3. That is my domain. That is just basic notation. That's set notation. That's not interval notation. If we wanted to get into interval notation, we would say this is 3 to infinity, and it includes 3, right? For right now, I have no problem with this answer right here. Okay, we solved for x. We said x minus 3, that thing under the radical, the radicand, it's got to be greater than or equal to 0. It can't be negative. Okay, so let's look at question 2. I bet you can guess how we set this one up. There's no square root with an x underneath in the denominator, so we don't even have to look at the whole dividing by 0, but there is a square root. So we take that radicand, negative x plus 2, and we say that has got to be greater than or equal to 0. Let's solve for x. We can do this a couple ways. I want to keep the x on the left because we read from left to right just naturally. So I'm going to keep the negative x here. I'm going to subtract 2 from both sides. So I've got negative x is greater than or equal to negative 2. And now I'm going to divide or multiply both sides by negative 1. So let's say I multiply by negative 1. Okay, so negative x becomes x, which is what I want. Negative 2 becomes 2. And remember, this is a little tricky one. If I multiply or divide by a negative, I have to turn the caret. I have to switch the direction of my inequality symbol. So my domain for the function g of x in question 2 is x is less than or equal to 2. Now, if you want that in interval notation, it would be negative infinity up to 2, and it did equal it because it's less than or equal to. Okay, I'm fine with either answer right now. We will eventually get into interval notation and require the interval notation, but for now, x is less than or equal to x is less than or equal to 2 is a perfectly good answer. Okay, all right, let's look at question 3. We should be getting a little bit better at these. Okay? Again, there's no denominator with an x, but there is a square root with an x in it. So we have to make sure that 4x minus 1 is always greater than or equal to 0. So we add 1 to both sides, and we divide by 4. So that tells me that my x, change the color up, my x must be greater than or equal to 1/4. Again, perfectly good answer. Standard notation. Okay? If you wanted to put that in interval notation, then that would be 1/4 to infinity. And it includes 1/4, so there's a bracket. Okay, so we've done 3 in a row where we had to look at square roots and how that limited a domain of a function. So now we're going to look at question 4, and I don't see any square roots. However, there is a denominator that has an x in it. So all I know is that that denominator cannot equal 0. It does not equal 0. So what is in the denominator? In this case, it's just x. X does not equal 0. Okay? So if you wanted to say this in standard notation, you would say x is all reals except 0. Okay? And there's nothing wrong with that. It's a legitimate answer. If you wanted to do this in interval notation, you would say from negative infinity to 0, but it doesn't include 0, so parentheses, and 0 to infinity. Okay, so this is everything but 0. Or you can say all reals except 0. Okay, I'll just put the quotation marks because I said you could say it. All right. Next up, number 5. There is a denominator with an x in it. That denominator, whatever it is, x minus 4 in this case, cannot equal 0. Solve for x. We add 4 to both sides. We get x cannot equal 4. So in words, you could write all reals except 4. Okay? This is not a plus or minus. That's a can't equal. Let's make that just a little clearer. Equals, nope. Okay? X is all real numbers except for 4. If you wanted to put this in interval notation, this would be negative infinity to 4, union 4 to infinity, with parentheses by the 4s because it can't equal the 4. Okay? It's everything else from negative infinity to infinity, but no 4. Everything but 4. Okay, those are pretty straightforward. Look at question number 6. Question number 6, again, there's no square root, so we don't have to worry about the whole, it's got to be greater than or equal to 0. But there is a denominator. So we have to make sure that the denominator does not equal 0. Okay, so let's solve for x. A couple ways you could do it. You could do this with factoring. You could say this is x plus 2 times x minus 2. If you recognize that x squared and 4 are perfect squares and there's a minus in between of them. So the difference of 2 perfect squares, you can do a plus b times a minus b. Okay. If you don't, let's solve the old-fashioned way. Let's isolate x by adding 4 to both sides. So we got x squared, keep the does not equal, add 4. Okay, now we got to cancel this squared. So we got to take the square root of both sides. When you take the square root of both sides, do not forget to plus minus the answer sign. So the answer is x is everything but plus or minus, and then the square root of 4 is 2. Okay, so if you're going to write out in words, you'd say all reals except 2 and negative 2. Okay, I'll say that again. All reals except 2 and negative 2. If you're going to do this one in interval notation, it's a little bit more fun because you got 2 things that x can't equal. So start at negative infinity and you keep going until you hit negative 2, but it can't equal it. And then you say, okay, it doesn't equal negative 2. We're going to go as far as 2, but it can't equal it. And then you're finally going to, I'm going to go to the next line here, say, okay, 2. Now I can go all the way to infinity. That's a 2 comma infinity, by the way. 2 comma infinity, okay? Don't get too hung up on the interval notation just yet. I mean, you should know what interval notation is, but as long as you can say x is everything, every real number except for 2 and negative 2, you're in good shape. Okay. So let's look at question 7. Again, all we're looking at is when we are going to limit the domain of the function. So we're only looking at these 2 things here, dividing by 0 or taking a square root that could be negative. All right, is there a denominator? Yeah, there is. So I know that the square root of 2x minus 3 does not equal 0. I know that, okay? How do I know that? Because that's in the denominator. Denominator can't be 0. I also know that there's a square root here. The square root tells me that that radicand, the 2x minus 3, just the 2x minus 3, I'm going to run into the other side here, but it's okay. That 2x minus 3, if we think back to questions 1, 2, and 3, that 2x minus 3 has got to be greater than or equal to 0. Okay? Now check this out. Because we've got a denominator that also has a square root, we can make this easier, or we can make this really hard. I think we should make this easy. So check what we're going to do. This says 2x minus 3, okay, the square root of 2x minus 3. If we square both sides, we just get 2x minus 3 does not equal 0, okay? If you just look at that and say, okay, it doesn't equal 0, I just have to remember that. Well, you come over here where it says 2x minus 3 is greater than or equal to 0, but I know it can't equal 0. All you need to do is take this and erase it. Okay? That's probably going to be the most difficult concept that we have here today, where we take these two and we join them together. All the square root is going to give you is this right here, right? But the fact that it's not equal to 0, right? You can either do this all out and then this all out and then just take what they have in common. That's the complicated way. Or you could just say, oh, that 2x minus 3, it can't equal 0 because it's in the denominator. So instead of greater than or equal to, it's just greater than because it's not equal to. So I don't even need to remember this anymore. Okay? I wouldn't say to erase it. You can cross it out or something. I just gave myself a little bit of room to write, actually. But the fact that I don't have this here doesn't make it any more difficult. It makes it, just one less thing to write. Okay? So I'm going to add 3 to both sides. Plus 3 plus 3. I'm going to go over here and start writing now. So I've got 2x is greater than 0 plus 3, which is 3. I'm going to divide both sides by 2. So I've got x is greater than 3/2. Okay. Standard notation, I like it, good stuff. If I wanted to write that as interval notation, it would be parenthesis 3/2, comma, infinity. Okay. But I'm not going to worry about that right now. Okay, all right. So I would go back, rewind that, maybe more than once for most of you, and just make sure that that you at least hear the concepts and see how they canceled out on that one. Okay, so we're going to finish with question 8 on this little topic. All right, so there's no square root on this one, which is kind of cool, but there is a denominator. So we know that this denominator, x squared plus 6x plus 5, the denominator cannot equal 0, right? Denominator can't equal 0. So when we solve for x here, now we're going to get into a little factoring. So it's a good thing we did the factoring worksheets before. Okay, so we've got two numbers that multiply to positive 5 but add to positive 6. So that would be 1 and 5. Cool. All right. So x plus 1 times x minus x plus 5 is my factored form. So now I've got x plus 1 times x plus 5 doesn't equal 0. Well, how do you finish that? Well, you split it and solve it. So it's just like when it said in last year, when it did say it equals 0, you would say x plus 1 equals 0, and then you'd subtract 1, and you'd find that x equals negative 1. Well, the only difference is there's a doesn't equal sign here. So we know x doesn't equal negative 1. Okay? So on this other half here, we know that x plus 5 doesn't equal 0. Subtract 5 from both sides, so x doesn't equal negative 5. Right? So when they say, what is the domain of the function? The domain of this function is every real number except for -1, and -5. If this were interval notation, it would be -infinity to -5, parenthesis, union, parenthesis, -5 to -1, parenthesis, another parenthesis, -1 to infinity. Okay, don't get hung up on that, but for those of you that are good with it, I just wanted to say it so you could verify that. Okay, so let's scoot down a little bit more and go to the next topic. So now we got piecewise functions. Piecewise functions are kind of cool because we can take different pieces of the x-axis or different intervals, like whenever x is less than 2, we're going to do this kind of funky function, and then everything greater than 2, we're going to do a completely different function. So you could have a line up until one point, and then all of a sudden you could have, a parabola after that point. So lines have certain types of equations. You know what linear equations look like, y equals mx plus b. And last year you studied parabolas with x squareds, quadratics, quite a bit in Algebra 2. So you shouldn't be too uncomfortable with the piecewise functions. We could put any type of functions in there. You're going to be able to do this. Okay? I don't have a lot of fears for you on this one. The domain one, work on that for a while. This one, I think we're going to be good. Okay, here we go. So a function is defined using 2 or more equations for different intervals over the domain. So they want you to evaluate the function when x is -1, when x is 0, when x is 1. Okay, so when x is -1, what does f of x equal? That's what they're asking. Okay, well, the first thing you need to know is when your x is in the right domain, then you can simply substitute it in like we did back near the beginning of the note with evaluating. Okay, so is this x, is -1 less than 0, or is it greater than or equal to 0? Hopefully, you're all saying to yourself, well, that's an easy question. -1 is less than 0. Okay, so we're going to use this top function to answer the question. We're going to say it's x squared plus 1. And what is this x? Well, the x is -1. -1 squared is 1, and 1 plus 1 is 2. So when x is -1, f of x is 2. Okay, we just answered first question. Let's look at the second one. When x is 0, what is f of x? Okay, again, we got to figure out which of these intervals we're looking at. Well, my interval has x being 0. So is 0 less than 0? Or is 0 greater than or equal to 0? Well, I hope you're all saying, well, duh, that's an easy one. It's greater than or equal to 0. Of course it is. Okay, so that means we're going to use this function rule for my x. So we're going to look at x minus 1. Okay, so what is our x? Well, our x is 0. So if our x is 0, 0 minus 1 is -1. So the answer to the second question, when x is 0, f of x is -1. The last part of this question says, what about when x is 1? So if x is 1, then what is f of x? Okay, first step, figure out which domain x equals 1 is in. Is it here or is it here? Right? Is x being 1 less than 0, or is x being 1 greater than or equal to 0? Okay, obviously it's greater than or equal to 0. So we look at this rule again. So we're looking at x minus 1. So what is x? X is 1. So we literally are going to say 1 minus 1, and it equals 0. So when x is 1, f of x is 0. Answered the question. Cool beans. Okay. All right. So we are going to look at this next little section. All right. When is f of x equal to 0? Don't make this difficult. F of x equals 0 means that f of x can be replaced by 0. We can substitute 0 for the f of x. So I'm going to take f of x. I'm just going to replace it with 0. So when it says, when is f of x equals 0? Well, let's figure it out. Let's find out what x will give us 0 for the f of x. Okay. Two-step algebra. Let's subtract 10. So I've got negative 10 equals negative 2x. We're going to have to divide by negative 2. Divide by negative 2. So I've got negative 10 divided by negative 2 is 5. Okay, these cancel beautifully, equals x. So when is f of x equal to 0? When that x is 5. Okay. And now let's look at this last question down here. Okay, when is f of x equal to 0? Well, let's call f of x 0 and find when it's true. X squared minus 5x plus 6. Ah, yes. So what can we do? It's not just x squared, so we can't take square root. It's a quadratic. It's a trinomial. There are 3 terms. So we have been factoring, which is great because now we can use a little bit of this factoring. Okay, the product is going to be positive 6, and the sum is going to be negative 5. So 2 numbers that multiply to 6, but add to negative 5. Well, if it's multiplying to a positive, it's got to be either plus, plus, or minus, minus, but they got to add to negative 5. So I'm going to go with negative 2 and negative 3. Okay. Negative 2 times negative 3 is 6. Negative 2 plus negative 3 is negative 5. Sweet. All right. Now, we're going to do what we did back previous page here. We're just going to split it and solve it. So x minus 2 could be equal to 0. X minus 3 could be equal to 0. That's a 3. Okay. So x minus 2 equals 0. We add 2 to both sides. So x could equal 2. X minus 3 equals 0. Add 3 to both sides. Or 3. So if we substitute 2 or 3 in for x, then we will find that f of x is 0. So f of 2 is 0, and f of 3 is 0. Okay. Last section. Okay. Again, don't make this difficult. When is this thing equal to this thing? Well, when you write it out and you solve it. So f of x is here. G of x is here. Okay, when are they equal? Well, let's set them equal and find out. X squared plus 1 is your f of x. 3x minus x squared is your f of x, is your g of x. Okay, so we got this one equals this one. Stick an equal sign there. Cool. Let's do it. All right. I see x squareds, right? And these do not cancel because one of them is positive and one of them is negative. So I'm going to have to add x squared here. So what is 1x squared plus 1x squared? That's 2x squared. Plus 1 equals 3x. So we got x squareds and we got x's. I think we need to get 0 on one side. All right. So I'm going to subtract 3x. Neither of these terms are like terms with 3x. So that means that when I subtract 3x from both sides, I got 0 here. This is going to be 2x squared minus 3x plus 1. So guess what we're going to do? I think you guessed it. We're going to look to see if we can factor. Okay, so let's look at product sum. Product sum. So we got A times C. Now, I don't care if you're doing slip, divide, and slide. I don't care if you were going to do grouping, right? Whatever floats your boat. I'm just going to do the product sum and see if it works. 2 times 1 is 2, so that's got to be the product. And the sum has got to be -3. All right, well, 2 is pretty easy. The only factors of 2 are 1 and 2. All right, now they have to multiply to give you +2, so they're either both plus plus or they're minus minus, and they got to add up to -3. So that means they got to be minus minus. Okay, so if I add them together, I got -3. Holy smokes, it looks like it's factorable. So we got to choose it. We got to choose, are we going to do grouping or are we going to do slip, divide, and slide? Okay. Just because this video is a little bit long, let's slip, divide, and slide this one. Okay, so I'm going to write 2x squared minus 3x plus 1 equals 0. All right, I'm going to slip. I'm going to slip this 2 to the 1. Okay. And that means we're going to go x squared minus 3x plus 2. We just got to bring down this equals 0. Okay. We have to factor it in the slip. We've already done the work, so we know it's going to be x minus 1 times x minus 2. Now we have to divide, because we did the slip, we have to divide. Okay. We slipped the 2, we're going to divide by 2. Okay, reduce your fractions if you can. 1/2 doesn't reduce. 2 over 2 reduces to 1. And now we're going to finish with our slide. Okay, there's a denominator of 2, slides over here, so I get 2x minus 1. Denominator is 1, so I don't really care about that. X minus 1 is 0. Okay, so now I got to finish by splitting and solving. So something times something equals 0. So if one of them is 0, it works. So 2x minus 1 equals 0 will work, and x minus 1 equals 0 will work. Okay, I'm going to give myself a little bit of space. All right, I'm going to add 1 to both sides. 2x equals 1. Divide by 2. So x equals 1/2 is one answer. I'm going to add 1. So x is 1 is the other answer. So let's look at what the question asks. Find the values of x for which f of x and g of x are equal. We set f of x equal to g of x, and we solve. So x can equal 1/2 or 1. Okay. All right, that concludes Unit 1, Day 1 notes. Okay? A lot of stuff in there, a lot of stuff. So, let me know if you have questions, but I really hope you go back and you watch parts of that video more than once. But reach out if you have any questions, if you need any support. Okay? See ya.